Hi, I'm Tommy Waalkes. I'm the Grand Circus instructor for Grand Rapids, and today I want to kind of talk to you about genetic algorithms and how they can be used for both game design and tackling some serious real-world problems. So before we go too much further, what I'd like to do is explain to you what exactly is a genetic algorithm. Simply put, genetic algorithms are based loosely off of the concept of evolution in biology. The idea is that the survival of the fittest and most adaptable are going to survive and pass their genes on. And in evolution, your one goal is to survive to reproduce, right? But there are very much many different ways and factors that go into dictating whether or not you survive long enough to have that offspring, right? Look at nature and notice how there were humongous dinosaurs at one point, and now we have small little itty-bitty squirrels, humongous whales, stuff like that, and there's a wide range of approaches and styles to tackling genetics. And the other thing is that there's not a single variable that really makes an animal successful. It's actually a whole array of different variables. So what does this mean in programming? In programming, the way that a genetic algorithm is going to work is we're essentially just going to say we have like a kind of a goal, right? And say we're just in a video game and the goal is to make it as close to the end of the level flag as possible. The approach that gets taken in programming is that we're going to have our video game character basically do 100 tries picking random different approaches and paths to that goal. And then at the end of the generation, say we do 100 runs, 100 tries, we're going to go through and judge what are our 10 best attempts. What are the 10 attempts that got closest to that goal? We're going to pick those and then create the next generation based off of those 10 most successful. Lather, rinse, repeat until you found several good approaches to getting towards that end goal. It's sort of the chimps on typewriters approach to problem solving. If you have infinite chimps on infinite typewriters, one of them eventually is going to belt out Shakespeare. Same idea here, but with getting to the end of a video game level. I wrote all of this in GameMaker. It was GameMaker 1.4 Studio, and it's a little game I call Square Wars. The idea behind it is the graphics are pretty simple because this is more about simulating and seeing cool situations and seeing them play out than it really is necessarily like a video game that you make meaningful decisions with. So when I set out to make this, there's a couple of rules that I set down to create my creatures. And in this game, the idea is that you're going to have little square creatures that all compete with each other to pretty much reproduce and survive. And there are going to be 3 different factions in this, and each faction is competing with the others. At the start, behavior and decisions need to be chosen largely at random. This is so we're just taking every possible different approach. Behavior and overarching strategy needs to occur on its own and be guided minimally as possible by the programmer. The idea here is that this imitates real life, changing and adapting without human interference. Faction number 1, that's going to be the humans, and they are the yellow squares and tend to have the most complex behavior. They'll have the weakest starting stats, generally speaking, kind of like lower hit points, defense, etc. But they tend to be the best later on in the game once they've had time to learn and adapt. So for example, when approached by an enemy, there's a chance that the human will charge the enemy or run away from them. And these chances and statistics are slightly randomized, and then passed on to their children, as if they're going and teaching the children these different behaviors. Humans will fight by shooting. This represents their ability to use tools, like in real life. And an interesting behavior that emerges from this is that instead of charging at the other factions, humans will actually run away and shoot at enemies that are coming up to them. And this is a behavior that kind of comes up on its own. I didn't program them to do that. The other cool behavior that you will see with humans a fair amount is that they'll sit still right next to these little food sources, which I have represented by trees. And they'll even form kind of cities, as it were. And the cities have several advantages. One, you have a ready supply of other humans to mate with. And then two, you have readily available food. And then three, there are strength in numbers. Since there's so many humans in cities, if they all shoot at once and cooperate, they'll have a much easier time of dealing with an enemy than if they were spread out. But since cities are densely populated, like in real life, there are some downsides. Namely, that zombies, if they get into a city, it can be nightmarish because there's so many humans all packed together and sitting in the same spot. So in short, humans have the most success if they're able to keep their population up and make it to the late game. So next, we have the alien factions. They're the little purple squares that reproduce very quickly. Humans, by the way, have 1 to 2 offspring per reproduction, so they build up slowly. But the aliens here, they produce double that. So they do 2 to 4 children per birth. And they have a very easy time building their population up and very quickly. The aliens attack and fight via hand-to-hand combat. They'll rush up to the other factions and attack them. And thanks to that, they'll tend to be rewarded for having higher movement speed, meaning they can close the gap against humans more quickly. Aliens, again, are best in early on in the simulation. The reason being is that they can get their numbers up quickly, and they generally tend to favor early and quick aggression. However, despite most aliens liking to be aggressive, there are actually other aliens that'll be a little slower and bulkier that tend to hang back and act as queens, as it were, and focus on reproducing and making more aliens. Alright, so next up we have zombies. Zombies cannot learn or pass behavior onto their children. Therefore, they're only existing in one of two different states. One, they wander around aimlessly, and then two, they'll rush and try and attack enemies. Aliens, like zombies, attack via melee combat. However, unlike aliens and humans, zombies don't reproduce by finding a mate with each other, but instead they reproduce by fighting an alien or zombie and passing their disease along. Anytime a zombie attacks an enemy, there's a small chance that they'll bite them. When put into this bitten state, the enemy is going to gradually lose hit points until they die. And when they do die, they'll return as a zombie based off of the statistics of the creature that just passed away. And those stats get a rough 50% buff. So zombies individually tend to be stronger, but their numbers tend to be some of the less stable among the population, just because their reproduction is totally based off of, chasing down other creatures. The next ability that I want to point out for zombies is that they'll sometimes, on death, explode and send out disease goo. This acts pretty much the same way that a bite does. However, there's a very tiny chance that this is going to mutate and make their host super strong. And then that host passes that super virus on to its children. So next, I want to quickly talk about what genetics tend to do well in the simulator. So unlike a typical genetic algorithm, one, this happens a little less structured and a little more organically. And two, instead of a typical genetic algorithm, you're only testing for a single factor of success. Who got the closest to the goal, who drove the fastest, right? Things like that. But in the simulation, we wind up caring about multiple different goals. And I'm going to list these off from most to least important. So first, reproduction. Pretty much just like in real evolution, if you survive long enough to reproduce, you're successful. 2, defeating enemies. And then 3, access to food. So reproduction, again, paramount, period. That's your goal. However, there's more than one way to reach that goal. The reason I put fending off enemies second is that they're the main competitor and obstacle to all the other goals, right? And then lastly, we have food. Food isn't necessary in the simulator for them to survive, but it does grant 2 benefits. 1, it heals them and strengthens that individual. And then 2, it lets them be able to reproduce a little sooner. Food is particularly helpful for humans just because their cycle of reproduction is so slow. Zombies don't eat the food since their food is the aliens and the humans. With all of this explained, here's some cool takeaways we can get from this project. And I'll attach it so you can play around with it for yourself. 1, creating a balanced competitive video game is hard. Just because one single variable, like doubling everybody's hit points, for example, could totally change the whole game. An example of this is the zombies in Square Wars. They were my problem children because they were either way too strong and just eating through all the populations way too fast, or they were way too weak and could never get close enough to pass the virus on. This kind of points to a point I'll make later on. 2, in the same vein, in ecosystems in real life, they're very complicated and delicate. I only had 3 creatures to balance in this, which are relatively simple in comparison to real animals, but there was a ton of code I had to write for even these very simple creatures. Now imagine what the effects of, say, taking squirrels out of the forests in North America, right? That would lead to a lot of very complicated and complex situations. How many other animals are affected? They lose a main food source or they lose a competitor. Next, complex simulations are going to be doable using this genetic approach. My ambition is to create something that actually mirrors real life ecosystems. And I would probably start with a more simplistic one with less variables, like the Arctic. There's fish, seals, and penguins. And also seeing how we can apply this and use this to analyze our systems in the real world. So things such as elections and economics, these would be really handy to understanding those complex and very open systems. Lastly, zombies. If there was an outbreak of zombies in real life, it wouldn't last very long. So we don't gotta worry about the zombie apocalypse. Basically, let me put it this way. Say you're a human and you needed to eat, but you had to go and kill a lion, which would say the main predator for humans. But the thing is you don't get any tools and you don't get any strategy. You just run right at that lion. That's it. That's all you got. And that's a zombie. You have to go and fight your main predator in order to reproduce. And that is a very much self-defeating sort of reproduction strategy. But more importantly, what could we do research-wise using these kind of zombie-like creatures? What could we do with like real diseases? How could we model their spread and observe their effects on populations? How could we see and detect the behavior of people in reaction to these diseases? Where exactly do we want to go from here? This is about the end of the video. So what I would like to do is I want to study genetics further and figure out a way to, based off of DNA genes, to develop a design pattern to make genetic algorithms easier. This would also make it a little easier to model, of course, real life creatures. Second, I'm particularly interested in how we could use genetic algorithms along with economics. Economics are going to be an open system, meaning anybody in the world can come in and start messing with stuff. So it's very hard to do experiments with economics in a realistic setting just because Lord knows there's so many different things that could happen. Thank you all for watching and listening to me throughout this video. Thank you to Grand Circus for giving me the opportunity to talk about this project. I'm excited and I really want to see where this can go. Like I said earlier, genetic algorithms have a ton of potential and I think we're just scraping the surface of what these could do and what data they could produce for us. So thanks again. I hope you all have a wonderful day, and I will see you later.